And I started out with looking at a system that could be described using Raoult's law, so we can keep the calculations as simple as possible. But today we'll be generalizing that into systems that are not obeying Raoult's law. So here's a picture of the problem. This is a slide from what we had in an earlier lecture. But there were usually one of four types of problems that we can be given to solve. One is where we're given the liquid phase compositions in either temperature or pressure, and we have to calculate the missing physical variable, either pressure or temperature, and the composition of the other phase. And the example 3 we were looking at were a case where we were given a vapor phase or a liquid phase composition and an unknown temperature. And now our fourth example, the one that I want to look at now, is this one where we are given a vapor phase composition. And this one, we're given a vapor phase composition and a pressure, and we want to calculate the temperature. That's generally the most challenging of the problems, but it's pretty simple as well. So let's take a look at it. Given a vapor mixture with Y1, remember we've got acetonitrile mixed with nitromethane here. Acetonitrile is a component 1, and that's got a vapor phase composition here of 0.6. He's looking at me, so I know what you're thinking.
That's fine.
And we're given that the pressure is 1 atmosphere. And as to determine the system temperature, which will be our dew point temperature in this case, we're talking about vapor phase properties, and we're talking about dew points, and the liquid phase composition here, X1 and X2. So we start out in a systematic way by writing the sum of the mole fractions in the system of unknown composition equal to 1. And then substitute in for each of those mole fractions here in terms of the relevant phase equilibrium equation, which is Raoult's law in this case. Then we rearrange the equation to be explicit for the system pressure. The unknown in this case is the temperature buried in Antoine's expressions for the vapor pressures. So while again in this simple case we might be able to just find a root for it by plugging in the Antoine expressions for the vapor pressures, it's convenient to set up an iterative procedure getting ready for situations that are more complicated where we need to do that. So what we do is we'll iterate on one of the expressions for one of the vapor pressures. So we isolate one of the vapor pressures, as I said here, for iteration. Here I've rewritten the equation, but I'll factor out P1S. So it looks like this, and in so doing, what I've introduced is this relative volatility of, in this case, is component 1 to component 2, which, if Raoult's law holds, is the ratio of the vapor pressures of component 1 to component 2. So when we clean that out, then we get the equation to iterate on is this. Or we'll iterate on the vapor pressure expression for component 1. Yes?
When you gave us that equation originally, you had it as alpha 2,1.
Yeah, in the previous example, it was
Oh.
alpha 2,1 was relevant.
Okay.
In this example, it's going to be alpha 1,2.
Thank you.
Yeah. So now to set up our iteration, we need a starting temperature, and what we did before was to just use the mole fraction average boiling point temperatures, as I've shown here. And that worked out to be 89.1 degrees C, so we can use that again. But anything reasonable is going to work, because the iteration is so fast that if you start out with this initial guess as for temperature that's pretty far off, it'll just take a little bit longer for you to converge into the result. So our procedure is to first calculate the relevant relative volatility, which in this case is alpha 1,2. Here it is written out for you. And then once we've got alpha 1,2, we can calculate the vapor pressure that we're iterating on. This P1S in this case, here it is. Here's the expression. And once we've got that vapor pressure, I can invert the Antoine equation for it and calculate the next value of temperature and then iterate this whole thing to convergence. And the spreadsheet looks something like this when you do that. So it very rapidly iterates and very rapidly converges. And the final temperature that we get here looks like is 90.85 degrees centigrade. And that will be our dew point temperature for this vapor mixture. And then we wanted the liquid composition as well. So I can write the equilibrium expression for X1, for example, Y1P over P1S. I've got P1S here already, so I can just plug that in and calculate that as 0.445. And of course, then the other mole fraction is just 1 minus that, or 0.555. So pretty straightforward. So I hope everyone is comfortable with doing this sort of thing. Now what we've been, let me talk a little bit here. What we've been doing is focusing on a specific dew point or bubble point temperature or pressure. In particular, what's of interest is our dew point or bubble point temperatures. If all we're interested in is the entire curve, let's say the dew point, bubble point set of curves, we don't have to use this procedure. We can just pick an array of temperatures, let's say from the boiling point of one component to that of the other, and then just solve for what the relevant vapor pressures and hence x of 1 and y1 are going to be. So let me show you that procedure. So this is now to generate a complete dew point, bubble point temperature curve. And I say here we can do it by calculating x1 and y1 values for a series of t's at the given pressure between our boiling point temperatures. So at each temperature we have our equilibrium equation for the total pressure given this way. And now I can rearrange that into, as we've got for the bubble point pressure, a linear function here of the mole fraction. And then I can rearrange this equation to give me an explicit expression here for the mole fraction of component 1 in terms of these now vapor pressures that I can calculate once I've picked a temperature. And as soon as I've got x1, I can calculate y1. So for our present case, let's say we've got the pure component boiling points are 81.1 for the acetonitrile, 101.1 for the nitromethane. So I can pick I just did it every 2 degrees here. I can pick whatever I want. And then just set it up to calculate each of the vapor pressures from the Antoine equations for those components. Calculate x1 out of this equation, and that gives me this column. And then I can calculate y1 out of this equation. I get this column. So now I've got the whole curve. This produces then my phase diagram here for the dew point and bubble point temperature. So I've got now another phase diagram. We saw one earlier where the temperature was held constant, and then we got dew point and bubble point values for the pressure. So we should understand that what we've got is a phase diagram here. So here at low temperatures we have a liquid, at higher temperatures we've got a vapor. The boundary line against the vapor phase is the dew point line. In this case it's temperature. The boundary line against the liquid phase is the bubble point temperature. And what we've got now is a split between the liquid and vapor phases, but in between these phase equilibrium lines, the dew point and bubble point temperatures, we have liquid plus vapor. So you should be clear and comfortable with that, with these kinds of diagrams. Now I've actually produced earlier the other one, so let's look at both of them here for just a moment. I've got a set of, in this case, dew point and bubble point pressures for a fixed temperature. Here I've got the one I just showed you, when I've got a fixed pressure, and I've got dew point and bubble point temperature curves here bounding these regions in the phase diagram. Now these diagrams contain essentially all of the information that there is to be had, including we can draw tie lines here. In this case, at any pressure, so these tie lines will give us, here what I've got for high pressure, I've got a liquid up here, so these are going to give me X values. These will give me Y values, because then I've got vapor down here at the lower pressures. So you can see if I drew a set of tie lines here, I would be getting a set of X1 and Y1 values. I could do the same thing here, drawing a set of tie lines, and I would get a set of X1, Y1 values now corresponding to an isothermal system. And so I could plot those. That's often interesting to look at the XY or YX diagrams. So here they are for the two systems we've got. The constant temperature diagram looks like this, and now let me explain it a bit. This is Y1 plotted against X1 for a given temperature of 100 degrees C. And this is the YX curve. And the 45-degree angle line is drawn in there pretty much just to guide the eye. And it's helpful when you're doing distillation type calculations, but it's common to do that. So that's what that is, it's nothing more than that. And what we can notice right away here is that component 1, this would be the acetonitrile in this case, is more volatile than component 2, which is our nitromethane. So that is expressed quantitatively in terms of this relative volatility. Now I'm going to give you what the general definition of relative volatility is. I've given you one that applies only to Raoult's law up to this point. So this is the general definition, and you really must know this. It's the y1 over x, the relative volatility of 1 to 2 is y1 over x1 divided by y2 over x2. And alpha 2,1 is 1 over alpha 1,2, so we see that. That's sort of obvious. Now for the Raoult's law case, alpha 1,2, for example, is just putting in for these values, P1S over P over P2S over P, P's cancel out, and I get the ratio of vapor pressures as you would expect, but not otherwise, as we'll see. That's what you get for Raoult's law. The general definition that is always true is this one. Well, I can get a similar diagram here at constant pressure, where I've got the y1 versus x1 curve at constant pressure, which are the tie lines for the phase diagram that I showed you for that. The dashed lines I put on just the rest of the information, so this will give us the total pressure curve. This will give us the temperature curve, both of them being bubble point values. Question about this? So let's consider this relative volatility as an important parameter. And it's evident that for the Raoult's law case, anyway here, that the relative volatility is going to be constant at a constant temperature, because vapor pressures just depend on temperature. Another thing we might see that if I have a constant pressure case, then the temperature is going to vary from one end of the composition range to the other. But if that variation isn't too great, both of these vapor pressures have somewhat similar temperature dependencies. Alpha still doesn't change very much, although it isn't, rigorously speaking, a constant. But if that temperature difference is not too great, we're kind of pushing the limit on the example that I've got, then we can assume that for all practical purposes, even for the constant pressure case, that the relative volatility can be taken as a constant. If that's true, then I can explicitly write the algebraic expression for the y-x curve, y1 as a function of x1, in terms of the relative volatility, taking it as a constant. And so this is the equation of the curves that you saw on the previous page. This is very convenient when we're doing some multi-stage distillation problems, to have an algebraic representation of the relative of the y-x curve in terms of the relative volatility. Now we can generalize the Raoult's law treatment to systems of any number of components using the same general procedure. And here I've got it all worked out for you. And I'm posting this. Of course, it will be in the notes, but I've also posted it in the figures. So this might be useful to you in homework problem or something, if you want to have a kind of a map to follow in order to solve any of these problems. Here are the first three types of examples. Over on the next page, I've got the last example. I don't think I need to go through this unless there are any questions. It's just generalizing now from 2 to any number of components, assuming the system can be described using Raoult's law. So now we get on to really interesting stuff where we don't obey Raoult's law, which is most of the time. So let's look at VLE behavior for non-ideal systems. This will bring up the issue of azeotropes, which I will be discussing here before long. So this is a diagram qualitatively similar to what we saw described using Raoult's law to describe the system. This is a bubble point pressure curve that we would get from Raoult's law in a straight line, as we saw earlier. But if Raoult's law does not hold, then one of two possibilities exists. Let's see if I can manage this without screwing it up. I might have something like that. Let's change it to, see what it's going to do with that. Doesn't like that at all, so let's try that again. There we go. I could have one of those possibilities, say, or the other. So I could have the total system pressure, or the bubble point pressure in this case, higher than would be expected from Raoult's law, and we call such things positive deviations. Oops, guess I better get on my pen again. Messed up. So from the standpoint of molecular behavior, if I have positive deviations, that means the components want to get out of solution more than they would if they obeyed Raoult's law. So that means that there's an incompatibility between these components to some extent. If I have the other situation here, then I'm going to call that negative deviations. And so we can describe these situations mathematically as follows. Of course, our equilibrium equation is equating the fugacity in the liquid phase to that in the vapor phase. And we're going to use the modified Raoult's law, but let's write the thing out here. So the fugacity in the vapor phase is given in general as the fugacity coefficient times the mole fraction times the pressure. But we're going to assume modified Raoult's law, which is equivalent to assuming, among other things, that the fugacity coefficient is 1. That is, we have the vapor phase is going to be described as an ideal mixture of ideal gases. That is inherent in the modified Raoult's law. For component 2, similarly, I have the fugacity coefficient for component 2 equal to 1. The fugacity in the liquid phase I'm going to describe this way in terms of an activity coefficient times the mole fraction times the vapor pressure. So what I've left out here in the general equation is any correction for non-ideality of the pure vapor phase. If I've already done this, that's certainly logical, so V1S would be taken as 1. And I've neglected the pointing factor because I'm assuming I'm not going to be having some huge pressures involved. And that's what results finally in the modified Raoult's law, which for component 1 looks like this, and component 2 looks like this. So the only non-ideality I'm embracing here is that is required to describe non-ideality in the liquid solution. And that is done in terms of these activity coefficients. The activity coefficients in general, let me just make some comments about this, are functions of everything, that is temperature, pressure, and composition. But the temperature and pressure dependencies of the activity coefficients are often quite small. So we can more or less ignore them. But we need to worry about the dependence of these activity coefficients, gamma 1 and gamma 2, on composition of the liquid phase. So now what I were interested in describing is one of these curves, which would be, these are, let's remind ourselves, bubble point pressure curves. And if I go through the procedure, that is, I write y1 plus y2 equals 1, write down the expressions for y1 and y2, in this case now using the modified Raoult's law, rearranging to solve for the total pressure. It's going to look like this equation. And it's very similar to the one I had before for the bubble point pressure, except now I've got these gamma guys in here. And that's a big deal. Now I should say something here about the general behavior, and that is that I'm never going to have the curve crossing this line. That is, it's either going to be above the Raoult's law line all the way across the composition range, or it's going to be below. And what that means is that the gamma 1 and gamma 2 are either both greater than 1 or either both less than 1. So for positive deviations, the activity coefficients are greater than 1, both of them are. For negative, they're less than 1, and both of them are. And we're gonna be able to prove that. Turns out that these activity coefficients are not just totally independent of one another. In fact, I'll be able to derive one from the other if I have knowledge of that activity coefficient as a function of composition. And we'll show that. I'm not sure whether we'll get to it today or possibly tomorrow. But for now, suffice it to say that this is the case. Now, what I showed there, these were bubble point pressure curves, but if I had, I want to get, I'm sorry, these are bubble and dew point pressure curves. If I want bubble and dew point temperature curves, then I've got another situation, then it might look something like this. Here we don't have a straight line, even in the case of Raoult's law. So I believe that for the bubble point curve, it looks something like this for Raoult's law. But I'm going to have something above it. This is hard to draw, get it looking nice, or below it for my dew point and bubble point temperature curves. So this top curve would be, what, that's my dew T curve, and this is my bubble T curve that I would have for that situation. Now, it's not uncommon for us to have, and I hope I've got something, now I've got to redraw it, for us to have deviations that are rather large. And by that, what I mean is that if I'm talking about a bubble point pressure curve, let's say it goes through a maximum on its way from one pressure to another. So I might have something, let's see if I can draw this without messing it up. I might have something like that. Now this is different than the others in the sense that I now have a maximum here. And that really is important. It gives us some interesting kinds of behavior. I've shown it here for the situation for positive deviations from ideality, but an equivalent situation, as I'll draw later, might exist for negative deviations from ideality. This curve that I've drawn is this is going to be the bubble point pressure curve. And I can see this is, when this exists, the system exhibits an azeotrope. This is the azeotrope point right here. And at an azeotrope, what I can write is partial of P with respect to x1, in this case at constant P, is equal to 0. That tells me I've got an extremum. If I had negative deviations, so that I had something, see if I can draw that. If I screwed it up, I might have something like this. Then I have it right here. Oops. But in any case, we can take that, the extremum in the system's pressure as a defining point for the azeotrope. But a more convenient one is as follows. If I draw the dew point pressure curve in, it has an interesting characteristic. This is what it looks like. Yeah.
Does that azeotrope, does that say the change in pressure at constant pressure?
Oh yeah, sorry. It should be at constant temperature. We have them both ways, but this one I'm drawing is constant temperature. And so what we notice is that these points at the azeotrope, the dew point and bubble point pressure curves, pass through the azeotropic point. So another thing is, let's say it this way, at the azeotrope, this is true, and y1 equal x1. And that fact is often used more often as a defining equation for the existence of an azeotrope. That is a point where the liquid and vapor compositions are the same. I would have a similar thing going on down here if I drew the curve in, it would look something like this. And this would be for negative deviations. Now, the fact is that a lot of systems exhibit azeotropes. If I have strong positive deviations, it's not too hard to get them strong enough, then the system will exhibit an azeotrope somewhere. And if I have strong interactions, strong positive interactions, such as complex formation between the components, I'll end up with negative deviations and likely an azeotrope. Now, an interesting thing, let's look at this top set of curves. So that's at constant temperature. At the azeotrope, I have a volatility reversal. So the y-x curve is going to look like this. If I were to draw instead of tie lines here, I've got tie lines here, but here I've got the vapor phase composition having the higher value of x1. Here is the liquid phase. So this is what the curve looks like. So another way to define the azeotrope is alpha 1, 2 equals 1. So all of these are equivalent statements defining an azeotrope.
What do the two lines in the graph represent? Not the bottom one, the one on the bottom.
This one?
Yeah. Yeah,
What does what represent?
the two curves.
Well, one is just to guide the eye. 45-degree line is to guide the eye.
Oh, and the actual and the okay and the
The actual curved line is the y-x curve.
okay, that makes okay. And the 45-degree line has no significant meaning.
That is a great significance. This is where the azeotrope is, and that's obviously then where y1 equals x1.
Okay, so where they intersect. But other than the intersection, other than to visualize the intersection point, there's no significant meaning to the 45.
I think it's pretty significant that the volatility reverses.
Yeah, I just meant it doesn't mean anything else. The 45-degree line doesn't mean anything anywhere else.
The 45-degree line, once again, is to guide the eye.
All right, thank you.
If I did it without that, it wouldn't be so obvious exactly where that azeotrope point is. And you'll find that a lot of graphical construction for doing simple distillation problems, which you will see in 435, depend on these constructions.
Will it be a 45-degree line in every system? Mm-hmm. In every system, okay.
Mm-hmm.
All right.
Unless you, for some reason, don't want a square diagram.
Yeah. That was my
Yeah.
question.
So it's going to turn out that we will involve ourselves quite often here with azeotropes. Now I don't have it attached right here. Oh, here I've got some azeotrope data that I've just thrown in for you to take a look at. And these are all isobaric data, that is a constant atmospheric pressure. And maybe we'll pull one or two of them out for a homework problem, I don't know. But anyway, there it is. Now, a common azeotrope, we can draw azeotrope curves on the temperature diagram as well. Let me clean this up and then just do that. So for the system with positive deviations from ideality, then the temperature goes through a minimum at the azeotrope. So this would be the corresponding temperature composition diagram. So this is what it looks like for positive. This is a little off, but forgive me for that. You see the idea that occurs where it's at a minimum. And these are called minimum boiling azeotropes with positive deviations. And there are a lot of them. The opposite is where it could draw, in fact, I'll leave this as an exercise. You could draw all of these curves for negative deviations as well, but an example would be, let me show one here. Oh boy, bad drawing. But this would be a positive, a maximum boiling azeotrope. And the classic example is ethanol and water, which has a maximum boiling azeotrope of about 95 degrees C. That's why you can't, in a simple distillation, purify ethanol beyond 95%. So it's the atmospheric azeotrope that determines the type of ethanol one can generally buy. If you want to go further, you have to do something to break the azeotrope, or you have to, once this is done, pull the water out with a desiccant or something like that. Now, let's look at the next really important issue. I wasn't sure I was going to get here today, but we did, which is great. So let me go on to the correlation now of activity coefficient data and the Gibbs-Duhem equation. Oh, wait a minute. Not quite yet. Activity coefficients from VLE data. Now the most important, where do we get these VLE data? I mentioned earlier there's no such thing as an activity coefficient meter, so we can't stick something in and determine what the activity coefficient is. And the most common way that we get that is from VLE measurements. We can calculate fugacities in gas phases, vapor phases. So once we've done that, we can look at what the liquid phase is, and at a given composition determine what the activity coefficient is. So that's the idea. Now there's a huge database for VLE data. And we find it all over the place, but you can find these, and they are of two kinds. There's a constant temperature database and constant pressure data, which are by far the more common. And they're almost all binary systems. There are a few published vapor-liquid equilibrium data for ternary systems, but they're very thin on the ground. It turns out that that's not much of a drawback, because as we'll be able to see here eventually, if we have understanding of the way the binary systems behave, that's good enough. We can predict ternary and higher number of component systems just out of binary parameters. We'll see how that works out. But for now, let's see how we extract activity coefficient values out of vapor-liquid equilibrium data. So here's data at constant temperature. I have a series of values of x1 versus y1. And this is at constant temperature, so the third thing we need to be given is the pressure. So here are the data that are given. There's 3 columns of data, x1, y1, and p, all at some given constant temperature. Now we use the modified Raoult law to calculate the gammas, so we can see here, for example, I can write gamma 1, just looking at it over here, is going to be y1p or x1p1s.